Okay, today we're going to be doing the derivatives of exponential functions. So we learned previously that natural exponential functions are of the form e to the power x. And if you graph this function, it looks something like that. It goes up like this. Now, if you were to graph the derivative, or the gradient of this function at all the different points, you would find the two graphs were identical because the derivative of e to the x is e to the x. And we'll run through a little explanation as why that is the case. So this is our y and this is our x. So let's consider a point here, x. And at point x, we've got f of x. And now we're going to go a wee bit further along, and we'll have point x plus some little increment dx. And so this is the function here, f of x plus dx. Oops, put the x bit. Now, if we consider dy by dx, so the gradient between, if we consider what is the gradient here, if we move x plus dx closer to x and get it closer and closer and closer and closer, we can think of what we're doing is we're narrowing down on the gradient on this point of the curve till it's so close it's like a point just right here at x. So dy by dx is the limit of dx heads towards 0. So as we make this little this wee dx part get closer and closer to 0, so this gap gets narrower, 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 is going to be the function f plus dx, so this bit function minus f of x over this minus this. So we're just using our little equation that we've always used to find the gradient between the grade. If we think about m is equal y at x minus y2 minus y1 over x2 minus x1. So this is our equation for the gradient, and our gradient is the same as the derivative. Now let's put in the function, the limit dx heads towards 0. So the function there is e to the x plus dx minus e of x, and then we'll just have dx. Then we have, because the x minus x cancel, just have dx there. Then as the limit dx heads towards 0, we can play around with this. This is the same as saying e of x, e dx minus 1 over dx. Now, if you consider this e dx minus 1 over dx for small values of dx. So if you just put some numbers into your calculator, so for point 1, e dx minus 1 over dx, that's meant to say the same as that, is going to be 1.051709. For 0.01, it becomes 1.005017. And you can see as we get smaller and smaller values of dx, we're getting this is heading closer and closer to 1. And you can keep going, and keep going. And what we're finding, whoops, meant to be a 0. That's meant to be a 0, 3, 4 zeros. There we go. This here, as dx tends towards 0, oops, write that properly, e dx minus 1 over dx will tend to go towards 1. Therefore, dy by dx is equal to the exponential of x. Let's consider if y is the exponential of some function. Now what we're going to do is we're going to use the chain rule. So let's let y equal e to the u, the exponential of u, where u is f of x. So dy by dx is going to be equal to e, the exponential of u, and du by dx is going to be the derivative of f. So dy by dx equals dy by du times du by dx, which is the exponential of u times the derivative of x, f of x. So that gives us d by dx of e to some function, the exponential of some function, is the derivative of that function times e to the f of x. And we can say in general, d by dx e to the ax plus b is going to be equal to a e to the ax plus b. Let's do a few examples to just clarify this a bit further and see how it works. So say I want to, so if y is equal to e to the 2x, the derivative is going to be, well, what if let's say this is going to be f of x, if f of x is equal to 2x, f dashed of x is equal to 2, so the derivative of this be 2 e to the 2x. Let's do another one. Let's do this function x to the e minus 5x. Now this is a function multiplied by a function, so we can use the product rule. So we've got u is equal to x, so du by dx is equal to 1. V is equal to e to the minus 5x, so dv by dx is going to be equal to minus 5 e to the minus 5x. And dy by dx is equal to u times dv by dx plus v times du by dx. So our function used x times the minus 5 e to the minus 5x plus v, which is e to the minus 5x times 1. So that is just going to give us, now what we can rearrange this. So we'll take e to the minus 5x out, and then that's going to, we'll take the minus 5x over here from this, and we'll put the 1 here from that. So make that a bit more neater. And let's do another one where y is equal to e to the 3x over x squared, and it's not going to be a surprise to know this is going to be the quotient rule. So we'll have u is equal to e to 3x, so du by dx is equal to 3 e to 3x, and v is just going to be x squared, so v divided by dx is 2x. And the quotient rule is dy by dx is going to be, let's just remind myself of the order. So v du by dx minus u dv by dx over v squared. So that gives us, so v is x squared times 3 e to the 3x, then minus u, which is e to the 3x times dv by dx, which was 2x, all over v squared, which is x squared, so it's going to be x to the power 4. Now we will tidy this up, so we will have 3x squared e to the 3x minus 2x e to the 3x, and then that's going to be over x squared. Now what can we take x4, sorry? So we're going to take an e to the 3x out. We're going to take as a x there and x there, so we'll take the x out, and that'll then give us 3x minus 2 all over x to the 4. So this will cancel with this, and we'll be left with, I'll write the answer here because I've run out of space, 3 e to the 3x minus 2 all over x cubed. Let's do one more, a wee bit more involved. So we've got the equation of a curve being y is e to the 2x minus 9 e to the x plus 7x, and we want to find the exact value of x coordinates at each stationary point and we want to determine their nature. So firstly we're going to be differentiating our equation for our curve. So dy by dx is going to be, 2e to 2x minus 9e to the x plus 7. And because we want to determine the nature of the stationary points, we're going to find the second derivative as well. So we'll differentiate this again. So it's going to be 4e to the 2x minus 9e to the x. Now, the stationary points are going to be when dy by dx equals 0. So this will be 2e to 2x minus 9e to the x plus 7 equals 0. Now, this is like a form of a quadratic equation. So we're going to factorise it. If you think about when it's e 2x, that's like this, the squared term in our quadratic equation. So we'll have 2e to the x and e to the x, and then we can have this is minus 9, so this will be of minus 7 minus 1, and that'll be then 2 plus 7 is 9, and well, minuses. So 2e to the x minus 7 equals 0. So e to the x must be equal to 7 over 2. And e to the x equals 1. So x is 0. And x must be equal to the natural logarithm of 7 over 2. So when x equals 0, the value for the second derivative is negative, because e to the 0 is 1, so that's going to be 4 minus 9, and that's a negative number. Therefore that's going to be a maximum. And when x is equal to the logarithm of 7 over 2, the derivative will be positive. Because remember that we're going to have, that's going to be the exponential and the logarithm will cancel each other out. So that will be a minimum. So I hope that helps.